Sixth period.
Hello, sixth period class. My name is Peyton Bell. I am introducing Mr. Debski. Today we are going to be talking about stoichiometry and limiting reactants. This is the bell work today. So, Mr. Debski.
Thank you, Peyton. Yay! They'll appreciate that. I do. I think they will. Okay. So, thank you for that. Now that's a great job, by the way. Bell work question is number 13 on page 983. Okay. So we've calculated the number of moles of nickel and HCl. We're going to divide the two. So I had a question in first period, and they said, "Can I just use these numbers? That one's bigger, so it's going to be excess, right?" No, because remember, these coefficients, the 2 and the 1, will change your answer. Sometimes they will, sometimes they won't. But you always have to divide or compare it to this ratio in order to figure it out. Okay, so don't take a shortcut. Don't think you found a shortcut. You can't. Now I'll tell you an alternate method in a few minutes. But right now, let's do it the way I've taught you. Okay, so we're going to take 0.085, divide by 0.069, and that's going to give me the ratio of nickel to HCl. And then I'm going to take, this is my given, so let's put that here in red. The given amounts are what I have to work with. What I need, according to the reaction, is a 2-to-1 ratio, or 1-to-2. I always double check. Okay, 2 HCl over 1 nickel, so that would be, in this case, 1 nickel over 2 HCl. They have to be in the same order, otherwise you get the wrong answer. Okay, this one's obviously 0.5 to 1. And this one, anybody correct that for me?
1.22.
1.22, thank you, Bella. 1.22 to 1. So, the question is, do I have more than enough or not enough of nickel? This is nickel.
More.
I got more than enough nickel. Okay, so the nickel is in the numerator, so that's the one I'm comparing here. I got more than enough nickel. It is excess. So I'm going to shrink this down a little bit so I can see more of my screen. Excess here. Limiting reactant here. Okay, so my hydrochloric acid is the limiting reactant. Step 1 done. Step 2, figure out what the second question is, number 13. Determine limiting reactant, the mass of the excess reactant, and the mass of nickel to, well, we're going to do 2 different stoichiometry things here. I need to figure out how much of this is produced. That's one of the questions. And then the last one, I need to figure out how much of this is used up. So I'll save that for last. First, we're going to do a stoichiometry problem starting with the 2.5. Cross this out because we're not going to use it right now. 2.5 grams of HCl. And then our 3 steps. 1, 2, 3. Get this big again.
You good?
Put it back. We'll put it back where it goes. Okay, so 36.5 grams in 1 mole. My mole ratio goes in this box right here, and it was 1, 2, 2 or 2 to 1. I just hate scrolling up and down 1,000 times on this thing. 1
It's 1
to 2. 1 mole of nickel chloride over 2 moles of HCl. And then the last step, change that into grams of nickel chloride by multiplying by the mole mass of nickel chloride, which is going to be grams of NiCl2 in 1 mole. Now for NiCl2, I need 2 chlorines, that's 35.5 times 2, 71. And 1 nickel, which I already wrote down up there, was 30, I didn't, up there. 58.7 plus 71, 129.7 or something like that. Okay. And then we get the calculator out, multiply 2.5 times 129.7, divide by 36.5, divide by 2. And Bella, what do you got?
4.44.
4.44 that word there, but it just helps me keep track of whether I got the right stuff or not. Okay. The other question in here is how much of the nickel or how much of the limiting reactant or the excess reactant is left over. So now I need to do one more of these, okay? Same 3 steps. That's right off the flow chart. These 3 steps that we do over and over and over again. When I look at your homework, I'm looking for that. I'm looking for the setup. I'm looking for step 1, molar mass, step 2, mole ratio, step 3, molar mass. Okay? And so this is called stoich. I wrote stoich on a lot of your homeworks, S-T-O-I-C-H. That just means I didn't see where you did the stoichiometry from. You found the limiting reactant, but you didn't calculate the problem. You didn't go ahead and finish the problem. So, in this case, we're going to start with 2.50 grams HCl. And I need 1, 2, 3 more steps. This time we're calculating the amount of nickel. So it's 36.5. The ratio of nickel to HCl was 1 to 2 still. So it's going to be the same ratio over here. 1 mole of nickel, 2 moles of HCl. But now we're calculating nickel, so it's just the 37 or 57 grams of nickel. No.
58.6.
Not 58.7. Alright, you got it. Hey, no. Oh,
Yeah, okay. I always have to stop and check my units. Sometimes I'll just stop and say, my units don't look right, and I double check everything. Just looking grams of HCl, grams of HCl, moles of HCl, moles of HCl, moles of nickel, per mole of nickel, yes. So in this case, this will tell me how many grams of nickel were used up, and then I subtract that from the amount I started with. Anybody got this number?
nickel is 58.7.
What's the answer? I'm not gonna change one a decimal, but I won't one time.
2.00.
Okay, 2.00, I had somebody calculate 1.99, so roughly the same thing. 2.00 grams of nickel react. That's not the final answer. The question is how much is left over. So we go all the way back to the top. And I started with 5, and I reacted 2, so the amount left over is 3. Okay, so 5.00 grams of nickel minus 2.00 grams of nickel used up equals 3.00 roughly grams of nickel excess. So if it asks you about how much excess is left over, you go back, you need to do one more stoichiometry using the excess amount and then subtract it from the original amount. If you get a negative answer here, you did something wrong. Okay, so again, you can't get a negative answer here. You either subtracted the numbers in the wrong order, or you did something wrong up here. Okay, or you calculated the wrong limiting reactant. Because sometimes if you do it backwards, you get the wrong limiting reactant. You're going to think you're reacting more than you actually have, and you can't do that, right? Law of conservation of matter. Okay, Bell-work question. Any questions on the Bell-work question? Long, but worthwhile. Okay, good practice. Practice, practice, practice. The more of these you can do this week, the better off you'll be come test time on Friday, because you'll be able to crank them out in 5 to 7 minutes instead of 15 to 20 minutes. Okay. Time is a major issue on this chapter when we get to tests. Okay, I can't give you 6 of these to do in one period, obviously. But on a test, I am going to want to give you 2 or 3. Okay, because you're going to have the basic stoichiometry problem, probably, at least one limiting reactant problem, and probably one with percent yield, which we're going to cover tomorrow. Percent yield is very quick, very easy. It's just one more step after this. Okay? As if you're not long enough. Now, take out the global warming sheets that I passed back to you. This chapter is math heavy, and because of that, I need a source for a lot of questions on the test, so I might pick some of these questions to put on the test on Friday. Just a couple multiple choice or short answer questions. So I want to go through the answers with you that I have. And this is what I have here. Let's just go through it quickly. Just double check your answers. If you got the wrong answer, just jot down something to remind you what the right one was. Everybody should know IPCC. That's an important thing because it's in the news all the time. Intergovernmental Panel on Climate Change is the correct answer. We talked about number 2 yesterday, money and jobs. Number 3, what does the data show for the temperature change during the Industrial Revolution? This is very fascinating. And again, I mentioned yesterday that in the 1980s, we thought, in the 1970s, we thought we were going into a global cooling phase where we were going to face another ice age. And that's because the temperatures dropped from World War II all the way up through the late 80s. So temperature was dropping. Even though we were polluting. World War II and afterwards was the greatest industrial output of the world in human history, when we were cranking out aircraft carriers and fighter jets and submarines and producing all that steel, and steel is a massive polluter, by the way. And it was before we implemented the, there's a branch of government that controls air emissions and stuff like that. It was long before we had air emission standards. So this doesn't make sense, okay? Great global cooling for half of the century before we ever got the global warming. The most important greenhouse gas, I didn't put it in here, but it is water, H2O, if you want. And that's because water is the most prevalent gas in our atmosphere, really, as far as a component. I mean, other than hydrogen and oxygen. Al Gore was the guy who kicked this whole thing off back in 2002, 2003. And here's the problem. The data shows that carbon dioxide always goes behind temperature change, not the other way around. Temperature change does not cause CO2. I mean, CO2 does not cause temperature change. Temperature change causes CO2. And that's what the data shows from all those ice cores. And you saw the guys talking about their data, talking about their experiments. And so it doesn't make sense. It's backwards. Okay? CO2, where does it come from? We'll see that in a second. How much CO2 do humans contribute? I put single digits. If you put something less than 10%, you're right. Okay? It's debatable how much that is because all these numbers are approximated. Nobody knows for sure how many volcanoes are and how much volcanoes are spewing into the atmosphere right now and how much CO2 is coming from farting cows and stuff like that. Seriously? Okay. Here's some of the sources. The oceans is the largest source of CO2 on the Earth. The oceans, of course, covers 3/4 of the Earth and has a huge amount of CO2 in it, carbon dioxide. But we also get huge amounts of carbon dioxide from volcanoes, animals, as I mentioned, cows. Some people are against cows because they produce flatulence, which is CO2 and methane. And methane is what a really, very bad gas for the atmosphere as well. Again, nobody's talking about methane. Bacteria, decomposition of vegetation, all these things produce CO2, as well as you and I, every time we breathe. Have some. Okay? What's the most likely source of climate change? Again, the sun and all of the different cycles it goes through. The sun goes through a lot of different cycles, sunspots, solar flares, and then secondly, cosmic rays and its influence on the clouds. This is an important one that I don't think has been really explored by scientists a lot. Cosmic rays are a part of the electromagnetic spectrum higher than what? Higher than even gamma rays. So this is super high energy rays, and they affect rainfall formation and cloud formation. Why does CO2 get blamed? A lot of different reasons. Basically a scapegoat. I wrote down politicization, medieval environmentalism. They mentioned some different things here. That's kind of weird. Patrick Moore, this is an interesting guy, co-founder of Greenpeace, was interviewed. Greenpeace is a major environmental group that started in the 1960s to fight against basically anything that was good. But those are the guys that go out and save the whales. They do some good stuff. Okay, but they're a little bit on the activist side. So activists from the socialist, communist camps moved into the environmental camp. This is very, very fascinating. It's a study in sociology. So these radicals, basically from the 1960s and 70s, ran out of causes. They couldn't fight the Vietnam War anymore, right? And so they had to find a cause. And the cause they found was global warming and environmentalism. So anti-capitalism, anti-globalization became the cry for their cause. Number 11, research and funding. I didn't put an answer here, but the answer is just money. How does it affect the debate? People's livelihoods depend on money, and money drives lots of things in our society, unfortunately. Computer models assume man-made CO2 is the main cause of climate change. Why are computer models not accurate? And every computer model to date for the global warming, the climate change thing has been completely off base. Every 5 years, every 2 years, every year they update the thing and try and tweak their model to match what the Earth is actually doing. The problem is you can tweak it to do whatever you want. And number 2, media. The news says, oh, the computer model is predicted plus such and such. We're going to die by the year 2050 because of blank, blank, blank. Okay? So again, computer models are useful, but only to a certain degree, depending on how good the science is behind the computer models. Is there really ice cap? Whoop, that was interesting. Is there really ice cap dangers? No. Okay. Sea levels are not rising any faster than they have for the last 100 years. Does the IPCC intentionally remove and edit its reports? Yes, one of the guys on the video said, hey, I used to write those reports. I wrote the report. They won't take my name off of it. And they've altered this, and they've altered this, and they've altered this. What 3 things happen if a scientist comes about in opposition to climate change? They lose their funding for research. They get accused of getting money from oil companies. And thirdly, their reputation is ruined. 16, what happens to the developing world that is morally repugnant? Okay, these are 4 things that are big factors in the third world countries like Africa, Southeast Asia, some of those countries. And the problem is they don't have electricity, right? It's hard to have a school when you don't have electricity. It's hard to have an educational system when you don't have electricity. It's hard to have people have the ability to get to work or to get to a place of education if they don't have electricity or energy. And so what the world is telling these countries right now is, sorry, if you build a power plant, you're going to pollute the atmosphere. We're not going to let you do that. So you just have to live in poverty the rest of your life. So sorry. Okay? And it's really wrong. This is really, really wrong. And there is, in some opinions, some racism built into this theory here. Okay? Number 17, write out the sentence from this time period. I don't know if it was my version or your version, but this is the sentence I want you to write down. The guy closed the whole video by saying this: it would be hilarious if it weren't so sad. And really, it's, if you look at the facts, just dig into it, spend some time researching both sides of an issue, and then find what the truth is. Okay? Anybody else? Questions? Alan, sit up, please. Let's take a look at some of the problems from last night. I left a couple on the board here, so take out your homework so I can check it, and then we will go over these 3 problems. Clipboard like this one, but not this one. Aha. Any questions about the research papers? Tomorrow you are going to have a 1-sentence thesis Should be like 3 points in that thesis. Please write it on a separate sheet of paper with the heading at the top. I'll probably collect it and give it back to you on Thursday. And your sources, okay? Minimum of 3 sources, not Wikipedia, should be listed on there. Just kind of like a little short starting bibliography. You can add to your sources over the course of the next month, obviously. You can change your sources, but you should have 3 starting sources. Just a quick question, because I did offer that you guys could use some of my resources on the back shelf there, but somebody took a book off that table back there. Did anybody borrow my book back there? I just want to know where it is. Okay? No? Big fat book? History of science, history of chemistry thing? I'm okay if you borrow stuff, you just need to let me know, and I don't want you to take it out of the classroom. Okay, so I'm looking for this book, brand new, $30 book. I don't like losing stuff. I don't want to spend an hour and a half looking back through video camera footage. Okay, homework. 3 problems last night, number 1, 2, 3. Colored your flowchart. Look on the back. So I was looking for your slide down here for these ones. So you should keep all your units in here. As well as to make mistakes, you won't be able to track it down, okay? Good. Same thing, keep all your units when you do these stoichiometry things. Good. 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 I like the little bar things. People do that. Some teachers do that. I don't mind that. It's fine. We went over some of yours this morning. Don't forget to write the reaction in here so you can constantly refer back to it. I don't see it for number 2. Oh, there it is. I got you. Good. Follow that right across. Okay, let's look at these together, okay? Number 1, check your work, check your answers, ask questions, okay? Number 1 is over here on this board, courtesy of Isaac McCrory. First thing, write out your reaction. Always write out your reaction. Number 2, balance it. Okay, so this one you should have 1, 5, 3, 4 for balancing. If you're not getting the balancing right, you're dead in the water. So get some help immediately, like from me or from somebody about balancing if you're not being able to balance these reactions. Okay, he did his balancing here. Number 2, he changed both of these into moles. His starting point was 14.8. and the other one was 3.44 or something like that. And write that down. I like to keep track of everything up here. So we're starting with 3.44 grams of oxygen and 14.8 grams of propane. So this is where I start with. He changed this one into moles, got 0.3364. He changed this one into moles and got 0.1075. Check your work. That's the first step. Got to start with moles. To find the limiting reactant, you take the ratio of those two and compare it to the coefficients of those two. So he did that right here. Here's what he has, 0.3364, this number, divided by this number. 0.3364 divided by 0.1075. He punched that in his calculator and got 3.128 over 1. The needed is a 5-to-1 ratio, but it's the opposite way around. It's actually, he did propane to oxygen, so here he's got to compare propane to oxygen. 1-to-5 ratio. 1 divided by 5 is 0.2, so we're comparing 3 versus 0.2. Those numbers are hugely different, and there's a ton of extra propane. You can tell it. I got 3 propane, I need 0.2 propane for every oxygen. So we got a huge amount of excess of the propane, and my limiting reactant becomes the oxygen. Any questions so far? Okay. Then he took the 3.4 grams of oxygen, okay, and he figured out how many moles of CO2 were going to be produced from this. This is my limiting reactant, so I ignore the 14.8 until I get to the very end of the problem. 3.44, change it into moles with a 32 molar mass. Ratio of 3 to 5. 3 to 5. You see why the balancing is important. If you balance it wrong, this mole ratio is going to be wrong. And this one just asks for the number of moles of CO2, not grams. Okay, so always read the question carefully. If they ask for mass, mass would be in grams. But if it says moles, you can stop short. 0.065 moles of CO2. Letter C, he went and figured out how much water is produced. So it's going to be the same process. 3.44 divided by 32. This time times 4 over 5. And this time times 18 grams for the H2O. So 1.55 grams of water are produced. And then lastly, how much of this is left over? So he's got to do a third stoichiometry problem. Okay, 3.44, 1 over 32, 1 to 5 ratio. This one here now. And then 44 grams for propane. That's 3 times 12 plus the 8. 36 plus 8 is 44. And 0.946. We would subtract the 0.946 from 14.8. And that would give me 13.8 roughly. 13.8 and 13.7. Something like that. And we can call it leftovers or excess reactant or whatever. Okay? When I'm looking at these problems, I'm looking for your stoichiometry. I'm looking for this right here. Okay, and there's a few of you that do it on separate lines. You do this part, and then you go to the next line, and you do this part. Don't do that, okay? Please, it's very hard for me to see, especially when we get to the test time. Okay, lay it out just like this with the 3 conversion factors, going all the way back to the very first problems we did, just basic stoichiometry problems. Step 1, step 2, step 3. Okay? So many of you are doing a great job. The neater this is, the easier it is to check your answer, the easier it is for you to find a mistake if you make a mistake. Also, units. I got a bunch of people leaving off. You just throw these numbers in here. Again, you're going to drive me crazy, and you're going to drive yourself crazy if you have to go back and check something. So please keep all the units in there, because I'm looking for, do these units cancel out? That tells me if you got the right numbers in the right place. The units are so incredibly important. Okay. Questions on number 1? Okay. Number 2 is over here, courtesy of Peyton Rickett. And 10 grams, 10 grams. Okay. We're looking for how much of this is produced, how much of this is produced, and how much of the excess is left over. Same 3 questions.
Bless.
Is that a sneeze? So, change this into moles, change this into moles, 10 grams of this, 10 grams of this, 0.034, 0.25. Here's what she has. Here's what she needed, 6 to 1, 7.4 to 1. Okay, so the sodium hydroxide is the one she has in the numerator. Do you have to have that in the numerator? No. You can do this upside down. You'll still get the same answer. So sodium hydroxide is definitely excess. Limiting reactant becomes the aluminum sulfite. That's the first answer. Letter B, we're going to do 3 stoichiometry problems. First one, stoichiometry, figure out how many moles of aluminum hydroxide. She got 0.0680. Looks right. The work looks right. I didn't double check all the answers. Second one, how much of the sodium sulfite is produced? That's a 3 to 1 ratio. Watch your mole ratio right here, 3 to 1. This one's 2 to 1 from the balanced chemical reaction. And lastly, how much of the excess is left over? So we need to do a third stoichiometry to figure out how much NaOH reacts. So, change it in moles, 6 to 1 ratio, sodium hydroxide to aluminum sulfite, and then 40 grams for the NaOH, 8.16. Subtract that from the original 10, and your answer is 1.4 grams of sodium hydroxide are left over. Okay. Questions on this one? Tomorrow, the last little twist we're going to put on this, and you'll see it on tonight's homework, and you can skip the part that says calculate the percent yield. But it's really easy. If in the problem, they're going to tell you one extra piece of information. They're going to tell you the theoretical amount that should be produced. So if they told you you were supposed to produce 14 grams here of this stuff, then tomorrow we're just going to take that number divided by 14 and change it into a percent by multiplying by 100. It's just one little step at the end to calculate the percent yield. Okay, the third one from your homework is, I didn't finish going through the last class. Let's take a quick look here. Courtesy of Ben Hines here. Let's see if we can decipher this a little bit. Okay, so as chemical reaction to the top and coefficients look balanced, 8 aluminums, 8 aluminums, 12 oxygens, 12 oxygens, 4 irons. Starting point 10.2 and 25.4. He changed them both into moles, and I got about here and then I started losing him. Let's see if we can figure this out. Okay? I'm going to review part of this. So what we have should have been 0.249 over 0.183. He told me he multiplied it by 9 for some reason, and I don't know why. And then we ran out of time. The needed amount of aluminum oxide to iron should be 4 to 4. Is that a 4?
That's a 9.
That's a
So,
9. I think it's a 21.
What? Say 21?
That's what I thought it was.
Okay, 4 to 4. But that's supposed to be a 9. Yes? 4 to 9. Okay, so what I would do is divide those two numbers. Some of you probably have it on your homework, so let's just double check his work here. 0.249 divided by 0.183, 1.36. So I got 1.36 to 1, and then 4 to 9 is 0.444. Everybody know your ninths? Oh, is it ninths or 11ths? I forget. 4 to 9. Yeah. So everybody, your 11ths decimals, right? What is 1/9? No, I meant ninths. 1/9 is 0.1111 repeating. 2/9 is 0.22222 repeating. 3/9 is 1/3, 0.33333333. 4/9 is 0.44444. 5/9 is 0.55555. 6/9 is 0.66666, which is 2/3. 7/9 is 0.77777. 8/9 is 0.8888. 9/9 is
No.
nope, it's 1.
It's funny.
Okay. So we're looking at the numerator, AL 203. Do I have more than enough or not enough? I guess so. Whoa. Okay. Stop. Okay. 2 things tonight. Worksheet 1 through 4. We did number 4 in class yesterday. So you can copy it or you can try and do it yourself and check your work against what we did in class yesterday. Do number 1, 2, and 3 as well. That's on the back side where it goes up to number 7. And then your sources and thesis statement on a separate piece of paper. You're dismissed. Have a great day.